In the last class, what we did in our last class?
We discussed about hydrocarbons, their nomenclature, and we also discussed molarity again, molar concept.
And did we discuss about the states of matter?
Yes, we did.
Okay. So let's start from there today. So what were the three states of matter?
Solid, liquid, and gas.
And what were the processes those were involved in the conversion of them? Like
For
what do
solid
we
to
gas? Let's start
yes,
with
ma'am.
solid to gas. From solid to gas conversion, what do we say that?
For solid to gas, melting. From liquid to
Solid,
gas, with yes, ma'am.
no, solid to liquid is melting.
Yes, ma'am.
I'm asking solid to gas.
Oh, sublimation.
Solid to gas is sublimation, right? This one is sublimation. Solid to liquid, you say melting,
Yes, ma'am.
right? Liquid to gas,
Liquid to gas, boiling or evaporation.
liquid to gas, boiling or evaporation. Gas to liquid,
Gas to liquid, condensation.
condensation. And finally, liquid to solid,
Freezing.
solid is freeze. Okay. Am I missing something? Or was this all?
Yes, ma'am.
This was all? I'm not missing anything, right?
No, ma'am. From gas to solid, it was desublimation. There was another.
Gas to solid, this is sublimation. Okay. Now moving on to the next topic. Next topic we have is classification of matter. Classification of matter. Now here we will classify matter into two things. One is mixture, another is pure elements. Okay, or pure
Yes, ma'am.
substance. Give me one second, let me connect my charger. Okay. Simrah. So we are classifying matters into two parts. One is mixture and another is pure substance. And furthermore, we are classifying this mixture into homogeneous, mixture and heterogeneous mixture. And pure substance, this we are classifying into two parts. One is elements, another one is compound. We haven't done it, right?
Yes, ma'am.
We did it?
No, ma'am, not yet.
Okay. So can you tell me any idea that what is mixture and what is pure substance?
Mixture is a uh, mixture is a combination of two or more compounds or elements together,
Mm-hmm. Okay.
which are classified into homogeneous and heterogeneous on the basis of their concentration and uniformity.
Mm-hmm. Mm-hmm. Okay. Very good. And what is pure substance?
Pure substances are elements and compounds existing in the purest form without any mixture of anything.
Mm-hmm. Okay. Okay. So you said the definition of mixture absolutely correct, as you said. Mixture is substance that contains particles of two or more pure substances. You also write down, okay?
Yes, ma'am, I am.
Two or more pure substances which may be present in a ratio or their composition might be variable. Okay?
Yes, ma'am.
Mixture, as we said, that we have divided it into two parts. One is heterogeneous mixture and another is homogeneous mixture. So do you have any idea what is heterogeneous mixture and what is homogeneous mixture?
In heterogeneous mixture, the pure substances which are mixed together are not in a well-defined ratio and are not
Mm-hmm.
uniform throughout the solution. There might be some particles which might be
Right.
visible,
Mm-hmm.
and in homogeneous mixture, the pure substances which are mixed together are in a perfect ratio and
Mm-hmm.
they are soluble with together. They are very, they can concentrate the mixture together very well.
Like
They are
the
soluble throughout the
ratio is
whole
uniform. The main point is they are mixed in a uniform ratio and the ratio is sorry, they are mixed in a fixed ratio and the ratio is uniform throughout the whole solution. Okay.
yes, ma'am. Yes,
So
ma'am.
if we try to imagine it, let's say this is heterogeneous mixture. is homogeneous mixture. So for heterogeneous mixture, let's say this was our particle 1. Here also, this be our particle 2. Then it will be our particle 3. And let's say we have another particle. So you see, in heterogeneous and homogeneous both the mixtures, now what we are doing, we are testing the mixtures. So for heterogeneous mixture, we are taking some amount from here and some amount from here. So you can clearly see that, let's say this is our 1, this is 2. So if we take the solution from 1, the first part, this part, the ratio of the elements, and if we take the mixture from the part 2, the ratio of the elements won't be same. In the part 1, we have a huge amount of these blue particles. In the mixture 2, we have a huge amount of these pink particles, right?
Yes,
So
ma'am.
the ratio will be same. But for the homogeneous mixture, let's say we are taking from here, or maybe we are taking from here, the ratio of all the particles are almost same, right?
Yes, ma'am.
This is what we call ununiformly distributed, and this what we call uniformly distributed. Okay?
Yes, ma'am.
Okay. So this is basically the main difference between heterogeneous and homogeneous mixture. So can you give me example of homogeneous mixture?
Homogeneous mixture. Brine solution. Table salt with water. NaCl plus water.
Right. Table salt plus water. This is a very good example of homogeneous mixture. Then we can have sugar and water.
Hmm. Yes, ma'am.
And another very good solution of homogeneous mixture is air. We know that in
Yes.
air, carbon dioxide, these things don't have to react, okay? It might not be soluble.
Hmm.
The mixture, it should be, the component should be in a fixed ratio and the ratio should be uniform. The fixed ratio should be same throughout the whole mixture. That's the whole point. It need not to be soluble, okay? It can be insoluble.
Yes, ma'am.
So here we have nitrogen, oxygen, those don't react to be soluble. If we have to say that this is soluble, those things, the solute and the solvent have to react, okay?
Yes, ma'am.
But it's not. So in air, like we have nitrogen, we have oxygen. Okay, it might not need to react actually. Okay, we will come to that later. Air, and then we have dust particles and all the elements, all the things are uniformly distributed throughout the whole atmosphere. Okay, but let's say
Yes,
if
ma'am.
we mix salt and sugar, yes, definitely we can make a homogeneous mixture of salt and sugar, but if we randomly mix salt and sugar, we will see that usually the mixture is heterogeneous. Fine?
Yes, ma'am.
Okay. Then coming to pure substances, in pure substances we have element and we have coming to pure substances. So what did you say? What is a pure substance?
Substances which are existing in their purest form. They're not forming any
Okay.
mixtures.
You are saying that exists in purest form, not forming any mixture. Okay. Okay. So first thing is it has to have a fixed composition. It has to have a fixed composition. Like, let's say how to differentiate it from the previous one. Let's say in the previous one, we have two amount of CuO and one amount of CuO2. Okay.
Yes, ma'am.
Uh, okay. And using these two, we are making a mixture such that the ratio of copper and oxygen is same throughout the whole mixture. Okay. We are keeping it in
Yes, ma'am.
this way. Call it a homogeneous mixture. But if we keep these two, CuO and CuO2 together, we can't call it a specific compound. CuO is a different compound and CuO2 is a different compound. So, as I said, the fixed composition. The composition has to be fixed. It either have to be CuO or it has to be CuO2. If it is both, then it is a homogeneous mixture. But if it is any one of them, then we can call it a pure substance, which in this case will be a compound. Okay.
Yes, ma'am.
Okay. Now, uh, for example of pure substances can be silver, gold. This is the symbol for silver, Ag. Au is the symbol for gold. And we can have sugar. When we are having only sugar, the easiest symbol for sugar is
Oh,
C6H12O6.
six.
You see, this is made up of different elements, but the elements are in a fixed composition, which is C6H12O6, right?
Yes, ma'am. Yes, ma'am.
It's not like that. At some place there are, let's say, 7 carbon, 12 hydrogen, and 6 oxygen. Another place 6 carbon, and another place 5 carbon, and these two be same. So if we average these three out, we will get it only. But this is not how it is supposed to be for pure substances. For pure substances, we are supposed to have a fixed composition. I am saying it again. Okay.
Yes, ma'am.
Then in under pure substance, we had two classifications. One was element. One was elements, and another was compounds. So what is elements and what is compounds?
Um, Elements
This
are
very consists of, yeah,
mm,
say what were you saying?
atoms only, consist of different atoms which are
Both
present
them
in
are consist of atoms.
not
Element
necessarily atoms.
consists
Mm.
of only one type of atom. Okay. These may exist uh, one type of atom, only one, not only one
Atoms
type.
or molecules of the same atom.
Yeah, not only one atom, it should be only one type of atom. It can be in the form of atom or it can be in the form of molecule. So let's say when we are talking about H2, This is a molecule, but it is consists of only one atom. Then when we have, as I said, silver, this is consist of only one atom as well as one type of atom, copper. Similarly, when, so, okay, now coming to compounds. What is compounds? Compound is
Different
consists of
atoms combining together to form compounds.
consists of
Two
fixed
or more.
composition
Hmm.
of two or more types of atoms. Okay. Okay. So it can be sodium chloride. This can be a compound. Yeah, I was using some of my compound. So example of compound can be sodium chloride, table salt. It can be H2O. Okay.
Yes, ma'am.
Okay. Then okay. After this, what we have two type of properties of a matter. What is one is physical property, another is chemical property. So can you tell me any idea that what is physical property and what is chemical property?
Um, Physical properties.
Mm-hmm.
Hmm.
Try?
They can be reversible reactions with physical properties.
No, no, no.
Um,
If there is any
no,
type,
that's a different topic. Hmm.
physical properties doesn't include any reaction. If there is a reaction, that means this is a chemical property. Okay. So physical
Hmm.
property are those properties that can be measured or observed. Okay. Measured or observed. That can be measured or observed without changing the identity, without changing the identity or composition of a substance. The physical properties are those properties which can be measured or observed without changing the identity or composition of the substance. Similarly, the measurement or observation of chemical property requires a chemical change to occur. So chemical property are those properties which requires a chemical change of the substance to observe or measure. Okay?
Yes, ma'am.
Okay. If I give you some properties of some substances, let's say acidity. Acidity means how much acid, the substances. Then we have boiling point. Then let's have basicity. Then what we can have, combustibility. Similarly, what more we can have? Okay, we can have color. We can have odor. Odor means smell.
Smell.
Yeah. Okay. And we can have another thing is melting point. So can you tell me that which of these are physical properties and which of these are chemical properties?
Acidity, basicity, combustibility are chemical properties.
This is acidity, basicity, and combustibility is chemical property, right?
Boiling point, color, odor, melting point are physical properties.
Very good. Can you explain it to me? What is combustibility?
Um, the way it reacts when it is burned or reacted with oxygen.
Okay, very good. So that is combustibility. So that is chemical property, right? And boiling point, color, melting point, odor, these are physical properties. Okay, very good. Next, coming to measurement of physical properties. So under measurement of physical properties, how do we measure physical property? What we did, we have fixed 7 basic units. Okay. So we have units. So you know what is unit?
Yes, ma'am.
Unit is the uh, unit is the fixed amount of any substance that we use to measure the other substances. Like let's say for gram, we have taken some amount of any substance and we defined it that it should be the definition of 1 gram. And based upon that, we calculate any multiplier of that substance. Okay. Like what is 1 kilogram? 1 kilogram is nothing but 1000 grams. Right.
Yes, ma'am.
Like for distance, let's say we have taken some distance and we have defined it to be 1 meter. We have taken a distance and we said that this should be 1 meter. And based upon that distance, we can measure any length. That how much multiply that distance is of the defined 1 meter. So if we are saying it something is 10 meter long, that means that that specific thing is 10 times of what we defined as 1 meter. Fine.
Yes, ma'am.
Uh, we have read about IUPAC, na?
Yes, ma'am.
Similarly, there are other scientific organizations. What they did, there is a museum actually. In the museum, there is a rod is kept there, and we have defined the length of the rod to be 1 meter. Okay, we have fixed it. 1 meter is something we have defined it. So we defined 1 meter, and keeping that thing fixed, we measure the other lengths. Otherwise, what the problem was, let's say some group of scientists were measuring in India and some group of scientists, let's say, measuring in England. Okay, so if their measurement scale is different, then if the scientist from India is saying 1 meter and the scientist from England is saying 1 meter and their 1 meter is not same, then they won't be able to communicate, na? So have a specific communication. They decided worldwide to have a specific definition. Thus, the idea of unit was introduced. Now, when the idea of unit was introduced, unit was divided into two parts. One was basic units and other were derived units. So basic units are those units which we can't break it down more. Those are the units using which we create other units. And those other units are the derived units. Okay. So basic units we can't break
Yes,
it
ma'am.
more. Right? Units are those units which we can create using those 7 basic units. So under basic units, let's see what we have. So firstly, under basic unit, we have mass, we have length, we have time, then we have mass, length, time, then we have electric current, then we have temperature, okay. We have mass, length, time, electric current, temperature, then we have, okay, this temperature is thermodynamic temperature, obviously. Then we have amount of substance, then we have luminous intensity. So these are the basic 7 units we have. These are all the basic 7 properties we have. We are noting them down, right?
Yes, ma'am.
Okay. So these are the basic 7 properties we have. Wait. Somehow it got removed. Okay, let me write it down. Electric current. Then what I wrote after that? I wrote
Temperature.
amount of substance. And finally, we had luminous intensity. So we denote these properties as, let's say mass we denote as M. These are the notations for the properties, not the unit for the properties. Okay. L we denote as,
Yes, ma'am.
length we denote
Yes,
as
ma'am.
L, time, small t, electric current, capital I, temperature, capital T, amount of substance, small n, luminous intensity is capital I, V suffix. Okay. Now coming to the unit, the SI unit. SI unit is a unit method or method to name the units which is acknowledged worldwide. Okay, all the scientists throughout the world use this unit. So mass is kilogram. So kilogram is the basic unit of the property mass in SI unit. Okay.
Yes, ma'am.
Okay. Inches, meter, time, second, Then we have electric current, which is ampere. Then temperature, we have Kelvin. Then amount of substance, we have mole. Luminous intensity is candela. Okay. And how
Yes, ma'am.
we note these units? See, these are the notations for the properties. Now what I am writing, these are the short forms of the unit. So kilogram, we know that we write it as kg. Meter, we write it as m. Don't get confused between this mass m and meter m, okay? When you come across any question or any definition, you will eventually understand that if it is implying mass or if it is implying meter, okay?
Yes, ma'am.
Okay. Then second, small is ampere, we denote as capital A. Kelvin, we denote as capital K. Mole is simple, we just remove the E. So this is MOL. Candela is small c, small d, CD. Fine?
Yes, ma'am.
Okay. So these are the basic units. So do you have idea about dimensions? Have you read it in physics?
Yes, ma'am.
Dimension, right. So if I ask you that what is dimension of mass, length and temperature, time, what would you say?
Together.
No, no, no. Mass, time and length. So uh, what is the dimension for mass?
It would be capital M
It would be
in
capital
mass.
M in third bracket, right?
Yes, ma'am. In square bracket. For time, it would be capital T.
Let me tell you one thing here. Do you know that any number, let's say we have 7, 7 raised to the power 0, what would be? It would be
1.
1, right?
Yes, ma'am.
Anything to the power 0 is 1. So we can write it as m, we can write it as m means m power 1, right?
Yes, ma'am.
Something that same number only. We can write it as m l 0, l power 0, t power 0. Because eventually these two will go to 1. So it will remain what it would remain. It would, m power 1 is m into 1 into 1. So eventually we will get back our this m. Na?
Yes, ma'am.
Fine. So we can write it in this way too. Similarly, tell me what will be for time.
M raised to the power 0, L raised to
Mm-hmm.
the power 0, T raised to power 1.
3 raised to 1. Very good. And what will be for length?
M raised to the power 0, L raised to the power 1, T raised to the power 0.
0. Right. So all these are the basic units. So similarly, can you tell me that what will be the this dimension for temperature?
M raised to the power 0, L raised to the power 0, T raised to the power 0, K raised to the power 1.
Very good. So these are the basic units. So these basic units means that in their dimension it will have only one term, right?
Yes, ma'am.
That means yeah, okay. As you said that this will be if I write the M, this would be M1, L0, T0, A. Electric current we denote as A. Sometimes we denote as I2. So A power 0, K power 0, N power 0. We can write it as mole too. Okay, let's write it as mole. Using mole. Mole power 0. Then IV power 0. Right? Similarly for
Yes, ma'am.
length, M will be 0 and L will be 1. Similarly here T will be 1. Here A will be 1. Here K will be 1. Here mole will be 1. Here IV will be 1 and all the others will be 0. Okay.
Yes, ma'am.
So this is about basic units. Now coming to derived units. Okay. One thing is this part is not in very detail in chemistry but usually I teach it because dimension is a very important concept. Okay. So if you understand the concept of dimension clearly, now if you forget some formula in the exam hall, or let's say you forget some unit, you can easily derive it. Okay. You know that formula that
Yes, ma'am.
if we are adding two properties or we are adding two units, if we are adding it, that means it has to have the same dimension. You know that rule.
Yes, ma'am. Principle of homogeneity.
Yes. So that means that if two things are getting added, their dimensions have to be same, right?
Yes, ma'am.
Now you tell me, I am giving you some physical properties and you will tell me their dimensions. Let me write it down. Try telling me the dimension of this 8.
Yes, ma'am.
Uh, Try telling me the dimension of this.
For velocity, it is L t raised to the power minus 1.
L T raised to the power minus 1. Very good.
For density, it is M L raised to the power minus 3.
Very good.
For concentration, I don't know. For acceleration, L t raised to the power minus 2.
Let's try doing concentration. What is the definition of density?
Density, mass upon volume.
Mass upon volume.
Mass per.
Concentration is amount of substance upon volume.
Hmm.
So can you tell me now what will be the dimension for concentration?
Amount of substance upon volume.
Amount of substance upon volume.
L raised to the power minus 3 mole,
Mole.
I think.
Correct.
Hmm.
Correct. Absolutely correct. Mole. L raised to minus 3. Acceleration is
L t raised to the power minus 2.
LT raised to the power minus 2. Area is
L square.
L square. Volume
L cube.
L cube. Electric charge.
I don't remember the formula to derive it.
Electric charge is, see, electric charge is amount of electric current flowed into time. So what it would be?
Amount of electric current flowed
Elec-
upon time
but into time.
into time. Uh, I T or
IT.
A
Very
T
yes.
I T
And heat.
heat ml square T raised to the power minus 2. Heat energy.
Heat energy, right?
Oh, heat energy.
Heat
Hmm.
is an energy, right?
Yes, ma'am.
So can you tell me what will be the dimension of force?
For force.
Force, yeah.
Force, it will be mLT raised to the power minus 1.
ml t raised to minus 1.
No, wait. mLT raised to the power minus 2. Sorry, I confused it.
Okay. So
Hmm.
did you memorize it all, or you actually understood
No,
how?
no, ma'am.
You
No,
understood,
ma'am.
right?
I do know the formula. Yes, ma'am. I'm done with the chapter. That's why.
Okay, okay, very good. Okay. So clearly, we had this definition like what is energy? Energy is amount of work done by a specific force, right? If we apply some force on some substance, the distance the substance moves, that is force, right? That is
Yes,
energy
ma'am.
or work. So clearly from here we can see that how we have defined work or energy. These are same thing we know by dimension, and
Yes,
we have
ma'am.
defined that work done by a specific force like displacement displacement took place upon applying a specific amount of force, right? This was the definition, no?
Yes,
This
ma'am.
was the definition, right? So clearly, if we define it in mathematically, so that means that force, that specific amount of force into displacement. So we can clearly see it from the dimension also, that this was the forward dimension of force, and if we multiply it with L, which is displacement, we clearly get the dimension of heat, which is a form of energy. Fine?
Yes, ma'am. Yes,
Okay.
ma'am.
Now uh, let you do a small task. Uh, okay. We have an equation AT squared plus VT plus C is equal to 0. Okay. Now I am telling you that T
Yes, ma'am.
implies time and C is some amount of length. Okay. So this C is some amount of length. This T is time. So can you give me the dimension of B and dimension of A?
Hmm. C is
We
length,
have to
right?
do
Hmm.
C is length, yes. We have to do it using the rule I told you.
Yes, ma'am. A will be LT raised to the power minus 2.
A will be L T raised to the power minus 2, right?
B will be LT raised to the power minus 1.
Minus 1. Very good. Okay. So we can confidently move forward. Okay. Now, another very important thing that I would tell you to remember. We know the amount liter, right? Liter is unit of what?
Liquid. To measure liquid.
To measure volume.
Hmm.
Okay. We measure the volume of the liquid using the unit liter, na?
Yes, ma'am.
Okay. So we have this unit liter. Now another unit of volume we have length Q, right? If we do cube of length, we get volume.
Yes, ma'am.
So I am telling you that 1 centimeter cube is equal to 1 milliliter. Okay.
Yes, ma'am.
1 centimeter cube is 1 milliliter. So can you tell me what will be 1 liter? Just a simple conversion. 1 centimeter cube is
Hmm.
1 milliliter. Then what will be 1 liter? If we try to convert the liter into something cube, what it will be?
1 liter will be how much milliliter, right?
How much? No, 1 liter will be how much centimeter cube?
Um, it would be 10
This
raised
is
to
hmm?
3 centimeter cube.
Okay, exactly. 1 liter is 10 cube milliliter. Now, this we know. And 1 milliliter is 1 centimeter cube. So 1 liter will be 10 cube centimeter
10
cube.
raised to, yes, ma'am.
And 10 cube centimeter cube, this we can write as 10 cube centimeter cube, we can write as what? We can write it as 10 centimeter into 10 centimeter into 10 centimeter.
Yes, ma'am.
That means 1 decimeter, right?
Yes, ma'am.
1 decimeter into 1 decimeter. So 1 liter means 1 decimeter cube. Okay?
Yes, ma'am.
Okay. This was another thing I had to say. And what is next we have? Okay. Next we have the thermometer conversion. So how many types of thermometer we have?
Yes, ma'am.
How many types of thermometer we have?
Thermometer, Fahrenheit,
Mm-hmm.
Kelvin, and centigrade, Celsius.
Okay. Centigrade, Fahrenheit. Let's deal with these two as of now. So what is the scale for centigrade thermometer? Where it starts and where it ends?
From 0, no, it can go negative as well.
Yeah, but the thermometer we use, it
Hmm.
goes to 0 degree centigrade
Generally,
to
from 0 to, yes, to
100 degrees.
100. Hmm.
This is the scale of thermometer. Fahrenheit scale goes from 32 degree Fahrenheit to 212 degree Fahrenheit, right? So if I ask you
Yes,
now
ma'am.
that we have some measurement, we have measured something, some substance in centigrade scale, and we get C. Let's say C degrees centigrade. And in Fahrenheit scale, we have measured some substance, we got F degree Fahrenheit. So what will be the relation between C and F? Can you tell me this?
No, I don't remember the conversion of centigrade and Fahrenheit.
Let's try now. Let's try how to do it. Let's draw two
Hmm.
thermometers or two scale. We don't have to draw exactly thermometers. Let's draw two scale. It will be our one thermometer. humidity or another thermometer. So the starting points are at the same points. So these are the starting points for the thermometers and these are the ending points for the thermometer. Let's say this is a centigrade scale, this is a Fahrenheit scale. So this is 0, this is 100, this is 32, this is 212. So how many sections the centigrade thermometers will have? It will have 100 sections, right? Like this, it will have 100 sections. And how many sections this scale will have?
180
This will have
sections.
180 sections. Now we have measured something and in centigrade scale we have get C and in Fahrenheit scale we have get F. So one thing we know for sure that the temperature C and temperature F are actually same. If we touch that temperature of like C degree centigrade if we touch and if we touch F degree Fahrenheit, we are going to feel the same amount of heat, right?
Yes,
So
ma'am.
let's say because we have measured the same substance. Let's say upon measuring the same substance here we are getting the temperature for both the cases. This is our C and this is our F. Okay,
Yes,
fine.
ma'am.
So what we have to do?
Yes, ma'am.
We have to equate these two. So for C, the for the measurement C, this is C only. So this is C plus 0, which is C. And for the Fahrenheit scale, it starts from 32. So it has to be F plus 32. Okay. Whatever we get,
Yes, ma'am.
it will be plus 32. Okay. Now, how many segments it has? It has 100 segments. Right?
Yes, ma'am.
No, that would be F minus 32. Wait. Because we are starting from 32 only now. So if our value is let's say 100, to get the actual value we have to subtract 32 from it because it is starting from 32 only. So it would be F minus 32. Okay. And here we have 100 sections. So if we divide it by 100 and if we divide it by 180, fine,
Yes, ma'am.
these two will be equal. Now if we simplify it, it would be C by 5 is equal to F minus 32 by 9. If we more simplify it, what we will get? We will get F minus 32 is equal to 9 by 5 C. That means F is 9 by 5 into C plus 32. So if we have the centigrade scale value C, equivalent Fahrenheit scale value, we will get this F, and the relation between these two is this. Okay?
Yes, ma'am.
Okay. So if I ask you a question that upon measuring it with the centigrade scale, the temperature I got 200 degrees centigrade, let's say 200 degrees centigrade. And now you measure it with a Fahrenheit scale. What will be the Fahrenheit scale value you will be getting? Can you tell me?
Hmm. 1 second. 392 Fahrenheit. Degree Fahrenheit.
390 degree Fahrenheit. Very good. And similarly, if I ask you that, let's say the Fahrenheit scale value we got, let me think of something. Let's say I am telling you the Fahrenheit scale value we have got 437 degree Fahrenheit. So can you tell me what will be the equivalent centigrade scale?
In the centigrade scale,
Mm-hmm.
uh, 125 degrees Celsius.
125. I guess you need to calculate once again. Let me calculate again. 437. You need to calculate again. How you are doing it?
No, sorry. 225 degrees
Okay.
Celsius. Mm-hmm.
Centigrade scale, you will
I
get
missed the two.
25 degrees centigrade. Very good. Okay. Okay. Fine. Another small thing I will be telling you today, which is, I guess you know it already, that how to do multiplication or division or something, or decimal numbers. So I am just giving you some decimal numbers. I guess you know it already. Can you calculate this 5 and tell me what will be the answers? Do you have a calculator?
No, I don't.
Okay, okay. Calculate these and tell me. Okay, then let me change the last one. Last one is a little not tough, but time taking. Just do these calculations and tell me. I just want to see if this concept is clear. You know the rules, right? Do I need to tell the
Ma'am.
rules?
No, ma'am.
Okay. Did you get the first one?
The first one is 6.75 into 10 raised to minus 3.
First one.
Yes, ma'am.
This one. This one. This one is for plus.
Yes, it is.
Say
No, I
it again. Why did
turned
you
into the 6.75 into 10 raised to minus 3. I turned it into the
say
standard form of
6.7?
significant figures.
The term I don't think you got it correct. See, it's 0. See it properly. 0.0037 and 0.503. Let's not
0.5067.
0.5067. Let's not apply significant numbers as of now. Let's just do the calculation. 0.5067. Yes. The next one. You don't have to apply the significant number theory now. Just do the calculation.
Second one will be 0.0001.
0.0001. No,
No?
no,
Is there another zero there?
no.
Ah,
See. First multiply, what are the numbers here? 25 and 4. First multiply
yes, ma'am.
25, 4. So what do we get?
100.
100. So let's write down 100 here. Now let's see how many numbers are there after the decimal. So after this decimal we have 3 numbers, right?
Yes,
So in
ma'am.
answer also we have to have 3 numbers after the decimal. So we have 100 here. So we will just simply put a decimal here. Okay.
Yes, ma'am.
Here we had 3 numbers after the decimal. So here we have to have 3 numbers after the decimal. And the answer we will finally get 0 0.1. Similarly, if we would have 0.0025 instead of 0.025 and we had to multiply it with 4, so what we would get? Again, we would get 100 first upon multiplying the numbers. Now here we had 4 numbers after the 0. So based upon that, we have to have 4 numbers after the decimal. We already have 3 numbers. So we have to put the decimal and put a 0 after that. Thus, we get 4 numbers after the decimal. Okay?
Yes, ma'am.
Okay. Do the third one.
The third one will be 0.015.
0.015. Very good. Fourth one.
Fourth one, 17.64.
17.64. Very good. And the final one.
16.
5.6 into 6.8.
Yes, ma'am. 16.
Yeah.
38.08.
38.08. So I am assuming this part is clear. We will end our class with a little math today. First question for the math here. This is from your book actually. So the question is, how many seconds are there in 2 days? So can you calculate and give me the answer?
Um, 2,880 seconds in 2 days.
2,800. How did you do it?
It's at 2 days, so 2 into 24 hours. So we need to convert it in seconds also. So into 60.
Wait. Into 24 hours after that?
Into 60.
Hmm. See, 2 days. Let's write down all the units. Otherwise, we will miss something. 2 days. That means 2 into 24 hours, right?
Yes, ma'am.
That means 2 into 24 into 60. This is not seconds. This is minutes.
60 minutes. So there will be another 61 seconds.
There will be another 60.
3,600 multiplied by 3,600.
This will be the seconds. So what it would be? What is the answer? The answer is
17,
1,72,800
1,72,800 seconds.
seconds. Okay. And another question is, a jug contains 2 liters of milk. Milk. What will be the volume in meter cube? So you understood the question? The amount
Yes,
is
ma'am.
given in meter. You have to deduce the amount in meter cube. So what it would be?
Is it 20 meter cube?
You are saying it's 20. Okay. I have told you that 1 liter What I have told you just some time ago. 1 liter is equal to
10 cube centimeter cube.
10 cube centimeter cube or 1 decimeter cube, right? You
Yes,
know
ma'am.
decimeter, na?
I did not remember the quantities yet.
Decimeter is
There
10
are many in
cent.
the table. Hmm.
Decimeter is 10 centimeter. And 10 decimeter is 1 meter. Okay, so let's do it with centimeter only. So 1 liter is 10 cube centimeter cube. So 2 liter will be 2 into 10 cube centimeter cube, right?
Yes, ma'am.
Now it means 2 into 10 centimeter whole cube. And what is the relation between centimeter and meter?
1 meter
100
is equal to
centimeter is,
100 centimeter. 1
yes,
meter.
1 is equal to 100 centimeter. That means 1 centimeter is 10 to the power minus 2 meter, right?
Yes, ma'am.
This is clear, na? 100
Hmm.
centimeter is 1 meter. That means, oh, yeah, 100 centimeter is 1 meter. That means 1 centimeter is 1 by 100 meter. And we can write it this way. So
Yes, ma'am.
we just do it. We have to 2 into 10 into, we have to replace centimeter with meter. That means 1 by 100 meter whole cube. So this will give us 2 into 1 by 10 meter whole cube. That means 2 into 10 to the power minus 3 meter cube or 0.002 meter cube. Kind?
Yes, ma'am.
So any doubt from today's class?